Welcome to this HP Expert 1 presentation. In this video, we are discussing the TCP IP transport layer with a focus on TCP and UDP, which are two protocols that reside at layer 4 in the OSI model, which are used by many higher layer protocols and applications. We're going to start off with a comparison of UDP and TCP, and I'll show you some of the differences between these two protocols. We're then going to discuss port numbers and terms such as ephemeral ports. Then we're going to look at the details of UDP and TCP, so detailed discussions of both of those protocols. I'd like to explain the TCP three-way handshake, windowing, and sequence numbers. Let's get started. Before discussing TCP and UDP, I'd like to remind you of the fact that IP, or Internet Protocol, is connectionless. Every packet is treated individually and separately by routers in a network. So if the PC is sending traffic to the server, individual packets from the PC could take the upper path to the destination. But at the same time, some packets may take the lower path. IP is connectionless. Traffic from a single session may be load balanced across multiple paths, and it may arrive out of order. So a single session or conversation could have multiple packets traversing different links and arriving out of order and with delays. That's to be expected in an IP network. In an ideal world, traffic will arrive in the order that it's transmitted. So PC1 transmits packet 1, 2, and 3, and it arrives at the server in that order. However, the packets may arrive in different orders. So packet 3 could arrive before packet 2. The server needs a mechanism to reorder the packets into their original sequence. IP also doesn't guarantee delivery of packets. So there's no guarantee that the packets will actually arrive. So the packets may arrive out of order, they may arrive with errors, or they may never arrive. The server needs to be able to handle those situations. So higher layer protocols need to ensure that reordering and checking of packets takes place to ensure successful delivery of data. The two protocols that we're going to concentrate on in this video is once again TCP and UDP, which are layer 4 protocols in the OSI model. In other words, they reside at the transport layer. Just to recap, at the physical layer, we would have physical specifications for Ethernet, RJ45, and other physical media. At layer 2, we have MAC addresses. On Ethernet, on WAN interfaces, other encapsulation types such as PPP and frame relay may be used. At layer 3, we have IP addresses. TCP and UDP provide different functions, but once again reside at layer 4 in the OSI model. To explain the differences, let's look at some analogies. Firstly, UDP, or User Datagram Protocol. UDP is connectionless. In other words, it does not guarantee the delivery of packets. It requires that higher layer protocols at the application layer ensure successful delivery of packets. As an example, an application such as TFTP, when transmitting data, will expect an acknowledgement of that data transmission. If the acknowledgement is not received, TFTP will retransmit the data. So TFTP at the application layer is implementing reliability. UDP at the transport layer is very similar to regular mail offered by the post office. You may, as an example, write a letter and enclose that in an envelope. By the same token, your data would be encapsulated in UDP. You would then post your letter, and hopefully the postal service will deliver the letter to the recipient. However, there is no guarantee that the letter will be collected, transported, delivered, and opened by the recipient, as this is regular mail. You as the sender do not get a read acknowledgement or proof of delivery of the letter. The Postal Service, once again, does not guarantee delivery and is not responsible for letting you know that the delivery was successful or unsuccessful. The advantage of this method is it's very simple and very scalable, but it has the inherent disadvantage of unreliability. UDP at layer 4 does not guarantee delivery. There is no delivery acknowledgement. There is no reliability. Higher layer protocols, once again, need to ensure reliability and acknowledgements if that's required. UDP does not provide those options or features. TCP, or Transmission Control Protocol, on the other hand, does provide delivery acknowledgement and reliability, but with the disadvantage of additional overhead. An analogy to explain the TCP three-way handshake and session establishment could be a telephone call between two parties. TCP is connection orientated in the same way that a telephone call is. If a person on the left makes a call to the person on the right is notified of the incoming connection or incoming call by the phone ringing. When the person on the right answers the call, they would acknowledge that by saying something like, "Hello, it's David speaking." The person on the left-hand side is thus notified that the telephone call has been answered. The caller would then say something like, "Hello, David, it's Peter speaking." So the called party, or the person on the right-hand side, knows who made the call. There's sort of a three-way handshake between the caller and called party in a telephone call. We have initiation of the call and notification, acknowledgement, and another acknowledgement. Please note this is just an analogy, and in a telephone environment, there may be many more steps that take place. But as an analogy, that's what takes place before communication starts between the two parties. Continuing with that analogy, if the party on the left-hand side wanted to provide some information to the party on the right-hand side, let's say a telephone number, the party on the left-hand side would read out the number, and in this example, I'm keeping it very simple, but imagine for a moment that it's a fairly long and complicated number. The party on the left-hand side would say something like, "The number is 555. The party on the right-hand side would then acknowledge receipt of that number by reading it back and saying the number received is 555. The party on the left-hand side would then ensure that the number was received correctly and would then continue with subsequent digits such as 1234. The party on the right-hand side would read those numbers back to ensure correct receipt of the number, so 1234. That's how we as humans can relay information via telephone and ensure that the data was received properly by the other party. Now, in TCP environments, the information is not echoed or read back to the sender, but there is the use of sequence numbers and acknowledgements to ensure successful delivery or successful receipt of information. Now, before I jump into the technical details of TCP and UDP, I'd like to firstly explain what a socket is, as this term is often used in networking, and I'm going to refer to it in this video. A socket is a combination of IP address of a host, in other words, the location of a computer, as well as the port number used. Port numbers are used to identify applications. Some well-known examples are HTTP, port 80, Telnet, port 23, TFTP, port 69, FTP, port 20, port 21. There are a lot of well-known port numbers, but there's some examples. And the transport protocol used, in other words, TCP or UDP. These three are then combined into a single entity in the same way a telephone connection is the combination of a phone number and particular extension. I'll be discussing TCP and UDP in the next few minutes. I'm then going to talk about port numbers and explain what port numbers do, and I've explained IP addressing in another video. The combination of these three is used to identify a connection between hosts. In Windows, you can view examples of sockets by typing the command netstat. So as an example, protocol is TCP. Here's my IP address and source port number, which is connected to Google using HTTP. HTTP once again uses port 80. So socket, IP address, port number, transport protocol, which allows for incoming data packets to be sent to the appropriate application, such as your web browser or telnet application. Now, TCP and UDP provide various features. One of the features is session multiplexing. This is where several message streams or sessions are multiplexed onto one logical link, and TCP and UDP keep track of which messages belong to which sessions. This would allow, for instance, one computer or host with a single IP address to communicate with multiple servers or multiple devices and have multiple sessions open at the same time. I, on this single machine, could open up multiple sessions to servers on the internet. So as an example, I've got a session to hp.com, to Gmail, to hp.com/networking. I have a single IP address, but I'm connecting to multiple servers simultaneously, therefore using session multiplexing. TCP in this example is allowing me to do that. I could, as an example, open up multiple sessions from my one machine to a single server, and each of those sessions would be maintained. The sessions are created and controlled within the network application, which contains functionality in the OSI model layers 5 through 7. When using a reliable service like TCP, a connection needs to be established first between the sender and receiver before any data can be transmitted. TCP will open up the connection and negotiate various connection parameters, including things like window size, which we'll discuss in more detail in the next few minutes, and that will happen before data is transmitted. During data flow, TCP will also maintain the reliability of the data and ensure that the connection is closed once the conversation has ended. UDP and TCP provide segmentation. Information may need to be segmented or broken up into smaller chunks for transmission across a physical medium. The maximum transmission unit, or MTU, of an outgoing interface depends on the physical media. So as an example, on a lot of interfaces, the maximum transmission unit is 1500 bytes. However, TCP, as an example, can theoretically support 65,495 bytes in a single packet. That's far greater than the physical media can support. So that packet needs to be broken up into smaller chunks or segments for transmission. The maximum segment size, or MSS, is the largest amount of data in bytes that TCP is willing to send in a single segment and is used to negotiate the smallest segment size to avoid fragmentation when sending traffic from A to B. So TCP will support MSS, so maximum segment size, and MTU path discovery to automatically determine the maximum MTU on a path between two devices. TCP will then only send enough data in a single packet to support the smallest MTU along the path and thus to avoid fragmentation of packets and the additional overhead associated with fragmentation and the putting together of the IP fragments. UDP, on the other hand, doesn't support this and expects higher layer protocols to put the fragments back together again. TCP uses flow control. UDP does not implement flow control. So with TCP flow control, we are trying to avoid a situation where the sender is sending data too quickly for the receiver to receive it and process the received data. So the idea is, if the processing power of the receiving device cannot handle the amount of data that it's receiving from the transmitter, It can tell the transmitter to slow down. The issue is, if the data is received quicker than the receiver can handle, the data will be dropped, which would require the transmitter to retransmit the data. Retransmissions waste time and network resources. And thus with flow control, the idea is to maximize the transfer rate, but try and minimize the requirements to retransmit. The idea here is don't overwhelm the receiver with the amount of data it's receiving. TCP basic flow control is implemented by the use of acknowledgements from the receiver in receipt of data received from the transmitter. TCP also uses something called a sliding window to control the flow of data. I'm going to explain this in a lot more detail in the next few minutes, but the idea here is we can regulate the transmission of data through a sliding window. UDP once again does not implement flow control, and UDP will merely send huge amounts of data even though the receiver cannot process the received data. UDP again relies on higher layer protocols to implement flow control. TCP is connection orientated, UDP is connectionless. TCP will establish the session connection and maintain the connection during the entire transmission. Once the transmission is complete, the session is terminated. UDP, on the other hand, does not set up sessions and will just send the data in the hope that the receiver will receive it. TCP implements reliability, where every segment transmitted is acknowledged, and if the segment goes missing, it will be retransmitted. UDP does not implement reliability, and once again will rely on the higher layer protocols to implement reliability if required. In certain cases, such as with voice over IP, reliability is not required. So there's no point retransmitting lost voice. So UDP is ideal for applications such as voice over IP. It's kind of pointless retransmitting lost voice. Here's a quick comparison between TCP and UDP. TCP is connection orientated, UDP is connectionless. TCP goes through the three-way handshake to form a session and then maintains that session or connection. UDP doesn't, it just sends the data, hoping that the data arrives. TCP, because of all the overhead, is slower than UDP. UDP, on the other hand, is quicker than TCP because it has less overhead. UDP does not set up sessions, does not maintain those sessions, there's no three-way handshake, there's no acknowledgements and sequence numbers. It's a lot simpler, therefore a lot quicker, but it's unreliable, whereas TCP is reliable. TCP acknowledges receipt of data. There's error checking and recovery. There's sequencing. UDP does not sequence, does not send acknowledgements. It has no recovery options. So if there's an error, it expects higher layer protocols to handle corrupted segments. UDP basically gives the reliability mechanism responsibility to the higher layer protocols. TCP implements flow control to make sure that the transmitter is not sending data quicker than the receiver can handle. UDP does not implement that. Now, which is better? Well, it depends on the application. With voice streaming and video streaming, there's no point retransmitting lost data. So UDP works well for applications where there's no need to retransmit, no need for sessions. TFTP is used for file transfers. It's similar to FTP in that it allows you to move a file from one device to another, but because TFTP uses UDP, TFTP implements a lot of reliability at the higher layers. FTP gives authentication, TFTP doesn't. FTP uses TCP for file transfers, TFTP doesn't. Applications such as HTTP and email also use TCP. UDP therefore is a transport layer protocol residing at layer 4 in the OSI model. It provides applications with access to the network layer without the overhead of reliability mechanisms. This once again is ideal for applications such as voice over IP or video. It's connectionless, where datagrams are sent to the destination without advanced notification. There is no communication before data transmission. The data will just arrive at the receiver, and it's expected that the receiver handle that data. UDP is capable of limited error checking. The UDP datagram does include an optional checksum value which the receiving device can use to test the integrity of the data. However, it's best effort and has no data recovery features. The UDP header also includes a destination port number, and if that datagram is directed to an inactive port on the receiving device, a return message can be transmitted to indicate that the port is unreachable. I will discuss port numbers in a moment in more detail. But the moral of the story is best effort delivery, no guarantee that data is delivered. Packets may be duplicated, they may be lost, they may be redirected. There's no data recovery in UDP. Once again, the higher layer protocols need to recover from lost or corrupted packets. As an example, TFTP has built-in mechanisms to handle data loss. TFTP has acknowledgements, retransmissions, sequencing, and other mechanisms to ensure reliability of data transmission because it cannot rely on UDP to implement that reliability. The UDP header is very simple. It has a 16-bit source port number, a 16-bit destination port number, a 16-bit UDP length. This field specifies the length or size in bytes of the entire datagram, in other words, the size of the header and data, and an optional UDP checksum. The minimum size or length of a UDP datagram is 8 bytes, because that's the length of the header. The maximum size, in theory, is 65,535 bytes. But IP version 4 has imposed a maximum of 65,507 bytes. So the datagram can be very small to very large in size. Port numbers are in the range 0 to 65,535. In a moment, I'll explain the difference between the ranges 1023, which are the well-known ranges, and some other ranges and port numbers known as ephemeral ports. But the moral of the story is that a source port is used and a destination port is used. TCP, or Transmission Control Protocol, is a transport layer protocol that is connection orientated, unlike UDP. It also allows higher layer protocols to access the network layer or IP layer, but in this case provides reliability. It's connection orientated. Before transmission, two devices have to establish a session. TCP generally implements a full duplex mode of operation. We won't go into some exceptions here, but essentially both sides can transmit and receive at the same time. This means, in other words, that a TCP connection is a pair of virtual circuits, one in each direction, which operate in full duplex mode. The transmitter can receive data at the same time it's transmitting, but both hosts can transmit and receive simultaneously. There's sequencing of packets to ensure data delivery. TCP segments are sequenced to ensure that the destination knows the correct order of segments received. If segments arrive out of order, they need to be reordered, and sequencing allows for reordering of the segments into the original order. Sequencing also allows the destination to determine if data is missing. The destination will send acknowledgements of receipt of data. So all data will be acknowledged by the receiver. If segments are not acknowledged by the receiver, the transmitter or sender will retransmit the segment or terminate the connection if it determines that the receiver is no longer involved in the conversation. So in TCP, there's sequencing, acknowledgements, error checking, and data recovery features. TCP is a reliable transport protocol. UDP is unreliable. As you can see, the TCP header has many more options than the UDP header. So to help with the explanation of the TCP header, I have captured traffic from my PC with IP address 10.0.0.6 to google.co.uk, IP address 74.125.233.87. So I initiated an HTTP session from my PC to Google, and I've captured that in Wireshark. So as an example here, you can see that my PC IP address 10.0.0.6 is connected to 74.125.233.87. I hope that by explaining this via Wireshark, rather than just showing you a screenshot of the header, you'll have a good understanding of how TCP works. So we're going to look at options such as the flags. Here you can see the SYN flag is set. I want to explain sequence numbers, window sizes, and a lot of the other options in the TCP header. At the end of this, you should have a good understanding of how TCP manages connections. Let's start with port numbers. There's a 16-bit source port, which identifies the sending port, and a 16-bit destination port, which identifies the receiving port. Now in the OSI model, when frames are received at layer 2, they are mapped to layer 3 using a type number on Ethernet 2, which is the most common type of Ethernet. So the type field identifies that this is IP version 4. The protocol number at the network layer identifies the transport layer protocol. So in the IP header, TCP or UDP is identified via the protocol number, and the port number is used to identify higher layer protocols at the transport layer. So the port numbers in the TCP header are identifying both the source and destination ports in a conversation. In other words, identifying the higher layer protocols. There are 3 groupings of port numbers. Ports less than and equal to 1023 are well-known port numbers. Some well-known examples are HTTP being port 80, TFTP being port 69, and so forth and so on. Registered ports are on the range 1024 to 49151, and dynamically assigned ports are on the range 49152 to 65535. When a PC initiates a connection to a server, it's going to use one of the dynamic port numbers. So as an example, it's going to use port 60,000 to connect to a web server with a destination port number of 80. So in the TCP header, you'll see the source port number and the destination port number. The destination port number is a well-known port number. The source port number is a dynamically assigned port number in the dynamic range. This server may be running an application such as IIS or Apache, which serves up web pages on the server. The PC would be using a web browser, something like Firefox or Chrome. This server application is listening on port 80, so the well-known port number 80 is mapped to the application. When traffic is received by the server, it's pushed to the application listening on that port number. In this case, IIS or Apache. Your web browser is listening on port 60,000. That's the dynamic port number that was chosen by the PC when initiating the session to the server. When traffic is returned to the PC, notice the source address is the server and the source port is 80. The destination address is the PC and the destination port is 60,000. The web browser running on the PC is listening on this port number. When you initiate multiple web browser connections to a server, each of those web browsers or tabs will use a separate port number. So here's an example using Wireshark. Notice the source address is 10.0.0.6. The destination address is 74.125.233.87. Opening up the layer 2 frame, which is Ethernet 2, we can see that the type field is set to 0x0800 in hexadecimal. That is the type value used for IP version 4. In other words, layer 2 is indicating that the protocol at layer 3 is IP version 4. Source address, once again 10.0.0.6, destination 74.125.233.87. Protocol is IP version 4. Notice here, please, the protocol field has a value of 6. TCP is referenced via the well-known number 6 in the IP header. So the protocol number for TCP is 6. Looking at TCP, we can see that the source port is 49.670 and the destination port is 80. So my PC has chosen a dynamic port number in this range as the source port number. The operating system that I'm using is Windows 7. So port number 49.487. If we open up TCP, we can see that once again. Destination port is the well-known port number 80, which is HTTP. Other information about TCP can be seen here. I'll talk about these in more detail in a moment. But notice here, destination port 80, which implies that the higher layer protocol is HTTP. In this example, my PC is sending information to the web server. So as an example, you can see the operating system being used. For the return traffic, notice that the source port is 80 and the destination port is 49.487. Opening up the data, you can see some data here. Let's look at something else. If we go through the options, so as an example here, notice once again source port 80, destination port 49491, and opening this up, you can see that there's some JavaScript over here. So opening this up, you can see that there's some JavaScript. The moral of the story is, when my host initiates the session, it's using a dynamic port number, connecting to the server on a well-known port number. The return traffic is returned with a source port number of 80, destination port number of the dynamic number that was chosen by the PC. Well-known port numbers are less than or equal to 1023, and here are some well-known port numbers. So as an example, HTTP is port 80, uses TCP, FTP port 21, TCP, FTP data port 20, TCP. So with FTP, we have two port numbers, FTP control, which is for the establishment and teardown of the FTP session, uses port 21. And for the actual data transfer, port 20 is used. Telnet uses port 23. TCP is the layer 4 protocol. DNS uses port 53, but both TCP and UDP are used with DNS. UDP is used by DNS to serve requests. In other words, when a host needs a name resolution for a domain name such as hp.com, that would use UDP port 53. TCP is used when the response data exceeds 512 bytes, and TCP is also used for tasks such as zone transfers. Zone transfers are used in DNS for the replication of databases containing DNS data across a set of DNS servers. TFTP uses port 69, but uses UDP. SNMP uses port 161, and it also uses UDP. So the IANA, or Internet Assigned Numbers Authority, is in charge of port numbers and their assignment. And as you can see here in this document, well-known port numbers or system port numbers are in the range 0 to 1023. User ports or registered ports are in the range 1024 to 49151. And dynamic or private port numbers are in this range. If you are interested in the differences, please read this RFC 6335. Let me show you some of the well-known port numbers. So if we scroll down, you can see FTP. Notice FTP data, FTP control, SSH, port 22, generally uses TCP. Telnet port 23, generally uses TCP. We can continue through the list and see the port numbers that have been allocated and registered. So let's look at one more. Here's HTTP, port 80. Once again, the full list of port numbers is available on the IANA's website. Another term you'll come across in networking is ephemeral port numbers. These are essentially the same as dynamic port numbers. They are short-lived ports used for the client side of the connection. Dynamic or private or ephemeral ports are only used for the duration of the session. The IANA once again suggests that range, 49152 to 65,535. However, different operating systems use different ranges. So BSD would use the range 1024 through to 4999. That changed in version 4.6 of BSD, when BSD started using the IANA range. Linux or Linux uses that port range 32768 to 61000. Windows Server through to 2003 used 1025 to 5000. Later releases of Windows, including Vista, Windows 7 and Windows 8, used the IANA range. So just be aware, the IANA recommends this range, but vendors don't necessarily always follow that range. That concludes this first video explaining the basics of TCP and UDP. In this video, we looked at the differences between UDP and TCP. I explained some basic concepts with regards to the protocols, and I explained port numbers. In the next video, we're going to look at additional TCP options, such as the SYN flag and the ACK flag, sequence numbers, sliding windows, and flow control. For more information, please go to hp.com/go/expert1.